Welcome back to the channel. We're going to start a new project today. We're going to build the Webster Engine Works 4-cycle gas engine. So this is an engine that the plans are actually free on the internet, so I'll put a link down in the description if you want to download them and follow along. So I've never built this engine, but I've read a lot about it on the internet, and they say it's a great first internal combustion engine, so it's easy to build. There's nothing real complicated about it, and it's considered a bar stock engine, so everything that we build is going to be from scratch. So there's no castings, so you can buy the material as you go, kind of as you build the part, so you don't have to put out as much money up front to buy a casting set. So first thing I want to do, we download the plans and printed those off. So we'll go through the plans just to get an idea of what we're getting into, see if there's anything that we, not sure about how to machine in, so we can be thinking about that. And then we'll start getting a list together of kind of what material we need to get started. So this is a 0.75 cubic inch engine. It's a 5/8 bore and a 1.25 stroke. So the first page here shows the base plate. This is aluminum, and it'll be the largest piece that's on the engine, and it's 4.938 by 8.125 inches, and it's 3/8 thick. So that'll be the biggest piece of aluminum we need to come up with. Generally, we're going to follow the plans as we build this engine as close as possible. One thing I will note that we will do different here is it cuts this notch out where the engine is. You can see this notch missing here, but I want to mount our gas tank here and potentially the coal. So when we cut this plate out, we're going to just leave this as a rectangle. So this is the side frame and the crankshaft support. So this will be the second biggest piece that we'll need to come up with, and it's 2.5 inches by 5 5/8, and it's 3/16 thick, which is a little bit harder to come up with. But one thing that we'll do, so we're going to actually end up with 3/8 plate that we will machine down to 5/16. So if you are looking for material, which we will discuss, you can find 3/8 stuff usually easier than you can 5/16. So don't be worried about absolutely getting a 5/16 piece. If you can find a plate that's 3/8, then we can always machine it down. So speaking of getting material, once we go through this and kind of get a list together, then we'll start looking for material. You can buy material online depending on where you're at. In the United States here, I've had pretty good luck with Speedy Metals. I've also had good luck with eBay, and that's usually where I go first. And you can type in aluminum plate or some different dimensions, and sometimes you can find what you need. But we need to go through our scrap bin first and see what we've got that'll already work, and then we'll figure out what we need to purchase. So the other piece here is the crankshaft support. So the crankshaft will go between these two holes, and then this piece is 2.5 by 2 1/8, and it's also 5/16. So here we've got the cylinder head frame. This is also aluminum, and this is 3/4 inch thick, 2 3/4 inches tall, and then 1.5 inches wide. So this is a pretty big chunk of aluminum here that we'll need to come up with. And then this is the cylinder, which can be 12L14 steel or cast iron. I have made engines in the past with just mystery steel, so if you don't know that it's 12L14 or you're not able to get that, if you can make it out of steel, it'll still work. One thing to note here, this piece, I cannot find on the drawing what the overall dimension is for this outside of this cylinder. So one thing we'll look at in a few minutes, there's actually some options online to download the CAD model for this engine. Somebody has a few different people have actually modeled this engine up. And you can download some free programs. We will look at Fusion 360, and then we will download this model and actually pull this up. And I've already done this and measured this cylinder here, and it's 1.5 inches OD. So what we need to come up with is 1.5 inches by 2.5, so it's 2 inches here, 1/2 inch there, piece of cast iron or steel in order to make this piece. So looking through the notes in the back for building this, the gentleman that drew this up suggested he used a dumbbell that he purchased for cast iron. So we'll look at that in a minute, but I did get a dumbbell that I think we can cut down enough to get this cylinder out of. So the flywheel, same thing, it's cast iron or cold rolled steel. So the same dumbbell that I think we can cut a chunk out of to get our cylinder, I should be able to cut down to this flywheel. It's 3 3/4 OD, and I'm not sure what the dumbbell is going to clean up at. It might be just a little bit smaller than that, but it'll still work to make our flywheel. We've got the crankshaft here, which is a single-sided crankshaft, and generally on the crankshaft here itself, I like to use drill rod. You can certainly turn a piece down, or if you have a piece that's pretty smooth, you can use it. But that's something that if you don't have, you'll want to look at purchasing a piece of drill rod for this crankshaft if you want to make it out of multiple pieces. You can certainly turn this out of one solid piece, but I think that's a lot of wasted material, so we're going to make it out of a piece of drill rod, and then we'll decide here if we're going to make this out of one piece or two pieces on the crankshaft throw. We've got some spacers here, cold rolled steel and some bronze. Moving on to the piston, it's aluminum. It'll be 5/8, so this is a pretty small piece of aluminum by 1 inch long. And then we've got a brass oil tube here that'll get pressed into the piston. We've got the connecting rod and the wrist pin and some wrist pin bushings and conrod bushings. So the connecting rod is a piece of aluminum, and it's not split on the big end. It just gets a bushing and gets captured on the crankshaft. So for a first engine, that does make it a lot easier to construct to make this, so you don't have to worry about drilling and cutting this cap off. So this will be one solid piece of aluminum, and then it suggests drill rod also for the wrist pin. So we'll need to come up with a piece of drill rod there. We got the rocker arm, which is a piece of steel. So we'll need to come up with a piece for that. We've got the spring, which is, we'll need to come up with a piece for that. We got the camshaft lobe, which is pretty small, so we should have a piece of metal for that. And then we'll have to make some screws. So the gears for this engine, it gives you some part numbers here for two different manufacturers. So if you're not able to cut gears for this engine, you can purchase the gears already, and then there is some modification to them after you purchase them, but you can get these. We're going to actually cut the gears for this engine. I've got the cutters for it, so we'll be making the gears, but if you're not able to do that, you can purchase the gears. So this is the valve block. You can see it here on the side of the engine. So there's three pieces that are stacked up on top of each other. There's a top piece that holds the intake valve and a bottom piece that holds the exhaust valve, and then there's a center section there that ties the two together. These are made out of aluminum, 1/8 inch thick. Here you can see the assembly. So we'll need to make some valve guides, and then the valves, which these are going to be made out of stainless steel. You can make them out of steel or stainless steel, but I've got some scrap stainless steel that we'll make these out of. You can make them out of a two-piece instead of one. I've never actually done that, but you can make the head and the stem separate and solder them together. Valve retainers, springs, gives the dimensions on the springs. We'll be making our own springs and turning these, but you could purchase springs also. The carburetor, so it gives plans for a carburetor, or if you're not able to make a carburetor, there are suggestions for using an RC carburetor. So there are some different part numbers, and if you search on the internet, there are some forums of some people that give some numbers of some carburetors that have worked for them. This carburetor supposedly works, but we're going to follow, there's another set of plans that we can download for free when we get to that point that we're going to make a different carburetor for it. Head gasket is just a copper or Teflon, or you could use just standard gasket material. We're going to make an oiler cup out of brass and a grease cup, which will go on the connecting rod, and then the exhaust. This is the adapter for the RC carb, so if you are going to run that commercially available carburetor, you'll want to make this adapter for it. There's an oiler here for the piston. So that covers all the parts. There are some good assembly pictures here of how the engine goes together. Two different side views. Here's an in view. And a top view. So there are some notes here that you can read through. There are construction notes that give you some good suggestions of when you're building each of these parts, kind of some ways to go about machining it, and some more notes. And this will get into actually setting the timing on the engine, and then it gives the following additional items that we need to put this engine together. So there's a set of ignition points, and it will tell you which engine, which car, and which engine to look up to get those, and a condenser and a spark plug. And if you want to run the crankshaft on ball bearings, it gives you part numbers for those ball bearings. We'll probably not run ball bearings. We'll just run a brass or bronze bearings. There are suggestions for piston rings here. We'll get into that a little bit later. If you want to purchase piston rings, you can. We'll probably run this engine on an O-ring instead of actual cast iron rings. There are some screws and some roll pins and cotter pins. So I did go online and I was able to find the points. These were $5.37. So I went ahead and purchased those just so we would have them. And I was able to find the condenser. This was $4.66. And I was able to find the spark plug. It's an NGK, a CM6, and this was $3.33. Little tidy guy. So aside from that, once I kind of looked everything over, then I got kind of got an idea together of what I needed. Started looking through my scrap bin. If you've been building engines for a while and you accumulate some scrap, that's always the first place that I try to look. So I was able to come up with a piece here that I think we can make the crankshaft support out of. And then I've got a small piece here that we can make the valve body out of. So this will be cut into 3 different pieces. And I was able to come up with a piece of scrap that we can make the front cylinder frame out of. All this stuff will have to be machined down to size. So I didn't have any plate for the bottom and for the side. So I was able to get this plate here off of eBay. It's 7 by 13 and it was $24. The actual plate itself was $10, but then it cost $14 to ship it. But this is big enough to get the base out of and our side, and then there'll be some stuff left over for additional material. So this plate, like the same as this plate here, it's 3/8 thick, so we'll have to machine this down to 5/16. And then I was able to get a dumbbell. This is a 12-pound dumbbell, but I think this will be big enough that we can cut the flywheel out of one side, and then we can cut a chunk out of this side to make the cylinder out of. I was hoping the center section here was going to be big enough, but it's a little bit too small to get the cylinder out of, but I think we can get it out of this end here. And this was $18 for the dumbbell. So once you get kind of download the plans and look through them, get you an idea of what we're going to be getting into. And because these plans are free, we'll try to go into a little bit more detail of how I machine, or what, the process we're going to go through to actually make this engine as we go along. The channel name is B Machining because my name is Brandon and a lot of people call me B, but it has a double meaning of BE machining to be machining. So in other words, to encourage others to be machining. So if you're looking to build a model engine, I think this would be a great engine to start with. It's going to be relatively simple build and relatively inexpensive, so you don't have to purchase an expensive casting kit, and the material is mostly aluminum. So I'd encourage you to download the plans and follow along. So the first thing we're going to do though is I want to get this dumbbell cut off here, and then I want to start turning it down. I want to make sure that it's going to work to make the flywheel, that it's going to not for some reason not be hard to machine, and that it doesn't have too much porosity in it to make the flywheel. So we'll get that on the bandsaw and cut it down. So just a little bit about bandsaw if you're not real familiar with bandsaw work. I have this chart here that came with the last blade that I purchased, and the first thing you need to do is pick a teeth count for your blade. So it gives a suggestion here of when selecting a number of teeth per inch in a bandsaw blade, consider the following. For hard materials such as iron and other metals, it is necessary to have at least 3 teeth inside the thickness of the material while cutting. For softer materials such as wood or cardboard, you can do more. Number of teeth depends on how fast you want to cut. So the more coarse the teeth, the rougher the finish, but the faster that it will cut. And a fine tooth configuration gives you a smoother finish and slower cutting speed. Also, depending on how wide your blade is, if you need to cut a radius, will depend on what the minimum radius that you can cut. So a thicker blade or wider blade is going to cut a larger radius, and then a smaller blade or narrower blade, you can cut a tighter radius. So what I've got on the bandsaw right now is an 18 tooth per inch blade. So if you do 18 tooth per inch, that means that the pitch is about 55 thousandths. So if we multiply that by 3, that would be roughly 165 thousandths would be the thinnest that you would want to cut with that. So it's enough to cut this cast iron. So once you get your blade picked, then the next thing you want to look at is how fast you're running the blade. So the feet per minute. This chart gives you some suggestions, and for cast iron, it suggests 100 feet per minute. So my bandsaw has 3 speed options. We're 80, 120, or 200 feet per minute. So we'll set that up, and we'll try 120. It's a little higher than what they suggest, but we'll try 120 feet per minute and see how that cuts. If we need to slow it down, then we can. So let's get this set up in the bandsaw and we'll get this piece cut off at the end here, and then we'll get this set up on the lathe and we'll start facing it off and see if we can get it turned down around and see how it's going to machine. Okay, so we're looking at the Webster engine model. You can download this for free from GrabCAD, and I'll put a link down in the description. And I'm using Autodesk Fusion to open this with. There's multiple programs that you could use. This one is free, however, for hobbyists, so it's free to download the model and free to download the Autodesk Fusion software to view it. So somebody took the time to model this engine up. There's a couple of different versions actually on GrabCAD. This one is just the first one that I grabbed. It looked to be complete, so we'll spin it around here and look at the model. So you can see the base plate and the side supports, and you can see how everything goes together. And with this, you can also hide different pieces of it. So if you don't want to look at the base support, or you need to look and see what something looks like inside of it, you can hide different areas. So you can use this to get an idea of what the parts are going to look like if you have a hard time looking at the blueprints or understanding how something goes together. This is a good resource to use. And what I used it for was, I couldn't find on the print what the diameter was on this, the OD on this cylinder. So I downloaded the model, and then you're able to measure directly to this. So we'll measure this cylinder here. And you can see the diameter is 1.5 inches. So then I knew how big I needed my cast iron piece to make that cylinder. So check it out. Like I say, you can download it for free, and you can use the Autodesk Fusion for free. And this will give you an idea of what everything is going to look like and how everything is going to go together. So we're over here at the smithy, and we're going to set this dumbbell piece that I cut off. We're going to set it up in the chuck here to face it, start facing it off. And first thing we need to do is switch out from our internal jaws to our external jaws. So if you've never switched the jaws out on your chuck, I'll go through the process here. So the first thing we need to do is get our old jaws out. So just screw them all the way out, and they pull out. So if you look at your jaws that you're going to put back in, they should be numbered 1, 2, and 3. You're going to put number 1 in first, number 2 in next, and then number 3. But if they're not numbered, and I'll show you how you can tell the difference here. If you stack them up, you can see that there's an offset in these threads. So this is jaw number 1, this is jaw number 2, and this is jaw number 3. So jaw number 1 will go in first, and then the scroll threads will catch it, and then we'll go around and then we'll catch scroll number 2. But number 1 here has already moved down some before the scroll comes around to catch this one. So in order for them to meet up in the middle, this jaw is a little bit farther down than this thread. And the same thing here, it's offset a little bit more. So once you screw the scroll all the way around to capture all 3 jaws, once they move the same distance to get in the middle, then it'll be centered up. So I've also numbered my chuck 1, 2, and 3. And I do that just so that every time I take my jaws out and back in, I get them back in to the same place. So if you've centered up on your tailstock for some reason, then that just helps to ensure that you get the same jaws back in the same place. They don't have to go into the same place, but I like to number mine. So we'll start with the number 1 jaw. So there's a number 1 here. And we've got the number 1 hole. So you can see the scroll there where it just starts capturing that one. So we back it up just a little bit. Put this jaw in. Turn it enough to where it captures it. So then we go to number 2, which I've got stamped number 2. Use the number 2 jaw. And we turn it till we see the scroll right there. And then that picked up the number 2 jaw. Then we'll turn it till we see the scroll. Back it up just a little bit. And put in the number 3 jaw. So if we did everything right, this is also a good time if you've got chips in there to clean the chips out of your scroll just to keep it clean. So if we did everything right, once we spin this down to the center, then all 3 jaws should meet. So you can see how all 3 jaws meet the same in the middle. So if you get one of them off, they won't meet right, so you'll need to take them back out and start over. So we should be able to set this up. We're going to face off. It's got a dome shape on it here, so we're going to try to set the flat side down here first. And we're going to set this up. I also like to tap it a little bit just to make sure that we're good and tight in the jaws. And we'll tighten it down. So the next thing we'll do is we'll get our tool set up to face this off. And I'm going to be using an insert for this just because it's what I've got set up right now. You could do it with a high-speed tool steel or an insert. Either one doesn't matter. The main thing we need to do is pick our speed. So this piece is approximately four inches from peak to peak. So I'll show you the chart here that I kind of use to get a starting point. And it's cutting speeds for common metals, and it gives you in surface feet per minute. So for cast iron, to figure out our speed, we want to do 4 times cutting speed divided by diameter. So for cast iron, it suggests 60. So we'll do 4 times 60, and then divide by our diameter, which is 4. So it suggests 60, which is pretty slow. I only have 6 speed options on my Smitty, so the lowest that I go down to is 160, so we'll run this at 160. If you're using an insert, ceramic inserts like this, you can run at a higher speed. So we'll start at 160 and see how that's cutting. So I was able to get the end of the dumbbell turned down to a chunk that we can use for the flywheel. It's still a little bit long. We'll need to shorten it up a little bit, and it ended up just a little bit small on the OD. By the time it cleaned up, there's one little space there where it didn't clean up good, but it's futile and small on the OD, but that's not a critical dimension for the flywheel, so it'll still work good. So I've cut another chunk out of the other side after I faced it off, and we're going to turn this into the cylinder. So I've made a punch mark on the end in the middle of it, and we're going to set this up in the 4-jaw chuck, and then we'll use this punch mark to get it lined up, and then we're going to turn this down till it's round, and it should end up at 1.5 inches on the OD, and then it's still a bit long. We'll face it off on the ends. We'll get this set up and turn it down so we can have a piece to turn into the cylinder. So we got this piece set up in the 4-jaw chuck, and in order to center it up, we've got a dead center on a dead center. So we got a dead center in the tailstock, and then a dead center between there to our punch mark. I've got a dial indicator on here, and we'll spin this, and you can see the dial indicator move. So we'll just keep adjusting the jaws until we get it centered in. Adjust them one at a time. Check it here, zero it, rotate it 180 degrees, and then split your difference, and then check it here. So we'll get it indicated in and then start machining on it. So that went pretty good. I was able to cut out a section of the other end of that dumbbell in the bandsaw, and then set it up in the 4-jaw chuck, and then turn it down to 1.5 inches. And it's a little bit still long right now, but this will work to make our cylinder. So we've got material for the cylinder, material for the flywheel, and then we've got plate for the base and the 2 side supports and the end frame, and then this for the valve body. So join us back next time. We will start marking out the plate to get it bandsawed out, and then we'll start machining everything to size. Thanks for watching.